Now for this question here, this is from topic 3, practice set 3. Given that y is equals to tangent ax, we're supposed to show that y prime is a plus ay squared. So what is y prime? Y prime here is actually dy dx. Okay, so in case you notice there's a scratch on my face, because my son scratched me, so don't worry about that. It's just an accident. Alright, so y prime here is actually referring to dy dx. Okay, so now and this, just in case you're not sure, this y prime is also another way for us to write down or express dy dx. Okay, so this question is just asking you to show that dy dx is equals to a plus ay squared, which is just involving some simple algebraic manipulation. Okay, it's not too difficult. Now my y is equals to tangent ax. Now we are supposed to differentiate it as first time, so dy dx, and we know that when we differentiate tangent, that gives us a secant square. Okay, so looking at this function itself, there are two layers. So first, of course, the outside layer is the main tangent expression function, and what is inside is the ax. So we need to differentiate outside, followed by the inside. So when we differentiate the first layer, the tangent, that will give us a secant square ax. Right, this is just differentiating the first layer. Right, so just let me just write it here, differentiating the first layer, and the second layer here, which is ax, differentiating ax will just give us a. That's differentiating the second layer. Okay, so from here, this is my dy dx so far looks like a secant square ax, right? And we're supposed to show that it looks like a plus ay squared. Considering what is y squared is tangent ax, right? So if you consider take a look at tangent, how can I have a tangent appearing here? So you know that this is supposed to look like tangent a plus ay squared. Alright, so just brainstorm a bit. What is a plus ay squared? This is like a plus a of tangent ax, okay, square. This is supposed to look like that. Your dy dx is supposed to look like this. So then I look at this, a squared, a secant square. How would this left hand side, what you have now, look like this? Alright, a plus a tangent square. So ideally you will see that what you would need in order to connect secant square and tangent square ax probably would be the Pythagorean identity. Alright, so using the Pythagorean identity, a secant square ax, this is like a tangent square. We know that secant square is tangent square plus 1, and we are done. Okay, you have shown that this is just a distributing in tangent square ax plus a, alright, which would just be a y squared plus a, and that would have allowed us to solve the first part. Okay, now second portion, now we're supposed to express y prime similarly as a polynomials in y, giving my answer in factorized form. So let's basically y double prime, what would that mean is this will basically refer to d2y dx square. We are differentiating it a second time. So let's go ahead and do it. We differentiate secant square ax again. So d2y dx square, that gives us probably again you see that if I consider secant square ax, this differentiating this like that, you can see that there's probably a chain rule that's involved. So this is a, let me write this as like a secant square ax, or I simply were to put the 2 outside in order to show you that there are a few layers lah. So the first layer of course would be that power 2, alright, that we need to take care of. So it's this power 2 that we need to take care of. This is the first layer. The second layer here would be secant ax, so that will be the second layer. And the third layer would be ax. The third layer will be ax. So there are 3 layers here. Alright, so let's differentiate the first layer. While differentiating the first layer, bracket to the power of 2, this will give us 2 multiplied by secant ax. And we just copy paste whatever that's inside. Now differentiating the second layer, which is the one underlined in blue, this is secant ax. Differentiating the second layer gives us secant. Remember, differentiating secant gives us secant tangent. Okay, so this is differentiating layer 2. Now green underline the third layer, the most inner layer, and differentiating ax gives us a. Okay, so now let me rewrite this secant and secant, that gives me a secant square. Now not forgetting there's an a here, so I'm just going to put another a here. So 2a square, simplifying this, secant and secant, that gives me secant square ax, tangent ax, tangent ax. And you can see how by really just utilizing what you have from earlier, I'm able to write this purely in terms of y, because we do know one thing, that is your, remember, secant square ax, right? This is tangent ax, this is just your y, and secant square ax basically like what we found earlier. We can write this as 1 plus y square, because this is just 1 plus tangent square. So with that, our final answer will just be 2a square. Secant square ax will be written as 1 plus y square, and tangent ax will be written as y. Let me just tidy this a bit, and you can see that I've actually managed to write my 2y dx square as a function polynomial in y. Okay, so that's all. Thank you for watching.